Introduction to Junction Field Effect Transistors, JFET. A transistor is a linear semiconductor device that controls current with the application of a lower power electrical signal. Transistors may be roughly grouped into two major divisions, bipolar and field effect. All field effect transistors are unipolar rather than bipolar devices. That is, the main current through them is comprised either of electrons through an N-type semiconductor or holes through a P-type semiconductor. This becomes more evident when a physical diagram of the device is seen. In a junction field effect transistor, or JFET, the controlled current passes from source to drain, or from drain to source as the case may be. The controlling voltage is applied between the gate and source. Note how the current does not have to cross through a PN junction on its way between source and drain. The path, called a channel, is an uninterrupted block of semiconductor material. In the image just shown, this channel is an N-type semiconductor. P-type channel JFETs are also manufactured. P-channel JFET. Generally, N-channel JFETs are more commonly used than P-channel. The reasons for this have to do with obscure details of semiconductor theory, which I'd rather not discuss in this chapter. As with bipolar transistors, I believe the best way to introduce field effect transistor usage is to avoid theory whenever possible and concentrate instead on operational characteristics. The only practical difference between N and P-channel JFETs you need to concern yourself with now is biasing of the PN junction formed between the gate material and the channel. With no voltage applied between gate and source, the channel is a wide open path for current to flow. However, if a voltage is applied between gate and source of such polarity that it reverse biases the PN junction, the flow between source and drain connections becomes limited or regulated, just as it was for bipolar transistors with a set amount of base current. Maximum gate source voltage pinches off all current through source and drain, thus forcing the JFET into cutoff mode. This behavior is due to the depletion region of the PN junction expanding under the influence of a reverse bias voltage, eventually occupying the entire width of the channel if the voltage is great enough. This action may be likened to reducing the flow of a liquid through a flexible hose by squeezing it. With enough force, the hose will be constricted enough to completely block the flow. Note how this operational behavior is exactly opposite of the bipolar junction transistor. Bipolar transistors are normally off devices. No current through the base, no current through the collector or the emitter. JFETs, on the other hand, are normally on devices. No voltage applied to the gate allows maximum current through the source and drain. Also, take note that the amount of current allowed through a JFET is determined by a voltage signal rather than a current signal, as with bipolar transistors. In fact, with the gate-sourced PN junction reverse biased, there should be nearly zero current through the gate connection. For this reason, we classify the JFET as a voltage-controlled device and the bipolar transistor as a current-controlled device.